to episode 11 of Q for Problems. Today's problem is problem 11 from the Project Euler problem set. So in this problem we want to find the greatest product of four adjacent numbers in the same direction. So that will be horizontally, vertically or diagonally. So you can see here in the grid we have the numbers 26, 63, 78 and 14 highlighted. And then if we do the product we get the number shown. So we want to find which is the greatest product of four adjacent numbers in this 20 by 20 grid. So let's have a look at the solutions. So in our developer, I have a function predefined g, which is used to generate a random x times x matrix of numbers. So if I define that, this is just so we can create a smaller matrix, so it's easier to visualize what's going on rather than the large 20 times 20 matrix that's given in the problem. So we'll say n assigned to g5. So you can see here it's just a random 5 times 5 matrix of integers between 0 to 100. And then we also have another input called x. That's going to be the number of adjacent elements we want to take. So in the question, that's 4. We're going to use 3 again because it's easier to visualize, just a smaller number. So to start off, we need to have the count of the number of rows and columns. So we're going to assume that the input is a square matrix. Always, because that is what's given the question. However, you could extend these solutions to handle any type of matrix, any shape, but we'll just make the assumption that it's a square matrix in this case, just to keep it simple. So you can see this is the count of the columns and the rows now. In this case, we're actually adding 1 on to the count and storing it in C, because we're going to be adding on an extra column in each case. So it's going to be a column of zeros, and I'll explain why we're doing that in a bit. So that's why it works. We're adding this 1 on to get the number of columns. So that'll make more sense when I explain it. And the next thing is to create a base index, which is going to be then scaled to get each of the directions. So this index is going to be created using a function described in episode 8. So check that out if you want to understand how this function works. But it's called C straight index, which is column straight index. So its first argument is the index you want to go up until, -1. So we want to go up until essentially how many rows and columns there are in total, how many elements are going to be in the flattened version of this matrix, which is R times C. So this will go from 0 to 29 essentially, because there's a count of 30. And then also how big each stride should be. So the strides, you'll see now what they are whenever I run this. So if I run, you can see that each stride has a size of 3, and each column is a stride. The first one is 0, 1, 2, then 1, 2, 3, then 2, 3, 4, all the way up to 29. So we're going to use this then to index into a flattened form of the matrix. And you can see that you already have the groupings of 3 here of adjacent elements. However, these values then will need scale depending on the direction we're moving in. So finally then we want to define a flattened version of our matrix. So that's going to be raise n. However, we're also going to have to do the joining before we raise it. So that will essentially be n join each left 0. So if I run that, you can see that essentially I've added in this 0 column. So now I'll explain why we have this. So if we look at our index, say we're all going in the horizontal direction in this case. So our first index will be 0, 1, 2, which will be these 3. The next one will be 1, 2, 3. The next one will be 2, 3, 4. After that, then we have 3, 4, 5. So if I didn't have that 0, that would actually be these 2, and then this, which is wrong. We don't want to overlap on the different rows, which is the case whenever we're using this flattened version of the index, or flattened version of the matrix and indexing in with this. So what I do is add on this extra column of zeros, because whenever we then have this 3, 4, 5, it's going to be these 3 values, which is going to essentially, whenever it does the product, will be 0, which is essentially nullifying this value, and it won't affect the results, because in this question we're trying to get the maximum. And then this will be the same then for when we move to 23, 0, 93, and then 0, 93, 90, or 9. Then the next valid one that doesn't have the 0 will be these 3, which is the correct next values. So that's the purpose of this 0 column, and we'll be doing that for each of the directions. So essentially, that is our flattened version Rn. So now we can actually simply work out the horizontal, which is just indexing into Rn with I. You'll see it's 66, 8, and 13. So that means that that is corresponding to these three. And you'll see then you can see these ones that have zero in them, but they'll be nullified out. So you can see if you look at each of these, you'll see it goes up then right up until 77, 69, 18, which is the second last one, and then obviously the last one is this nullified one again. So we will mark this with a H just to let us know that this is the horizontal one, and we'll move on to the vertical. So if we look at our original n matrix, to get the vertical can actually, if we flip this matrix, we can actually just treat it the exact same as the horizontal, because when you flip the matrix or transpose it, the columns, i.e. the verticals, will essentially become the horizontals, and then we just need to do exactly what we did here before. So the first thing to do then is to flip n, get the transposed form, and as you can see now, the horizontal is what the vertical used to be. And then because we're using the original n here, not the rn, which already had the raising and the join done, we have to do that again. So we essentially join our zero onto each column again, just as we had before, for the exact same reason. And then we need to raise this to get the flattened version, and then we can just index with I. And you can see then that this gives us our vertical grips. Moving on now to the diagonals, we first need to create a diagonal scaling. So if I look at the original n again, how is the diagonal defined? Well, if we think about the horizontal, and we'll use the first index of the horizontal, 0, 1, 2 here. The diagonal, the very first diagonal will be these three. So it's essentially the same as the very first item, so 0. Then the second item is actually the second item of the horizontal moved down one row. And the third item then is the third item of the horizontal moved down 2 rows. And that's a similar pattern then across all the different ones, and will actually be a similar pattern then going the other way. But we'll talk about that in a minute. So we need to actually create some kind of scaling to scale in this manner. So that will be ds, we'll call it, and it is simply c times till x. So if I run that, that gives me 0, 6, 12. So think about this is at the 0th index. Then this is going to be 1, 2, 3, 4, 5, 6. So there's 6 places between it and the next item. And that is then the same. There's another 6 between it and the third item. So that is how the scaling is created. And we also have the problem then that if we look at our I, which is what we're going to be scaling, a lot of these indexes are above 18. However, when we add on, say, 6 or 12 to some of these values, they're going to go beyond the range. Now in Q, we can index outside a range and it'll just return null, so that's not a problem. However, just to avoid having to do all the extra work, because if this is a larger matrix, there's going to be a lot more columns here, we can simply just drop some of these items. So the drop is, I save it in a variable called d. It's going to be neg on c times x minus 1. So that tells us how many items need dropped from the end, how many of these columns. So if you think about it, the 12 will be these 3, 6, 9, 12. And then the very last one's going to be 17 here. So if you add on 12 to that, that's going to give you 29, which would in effect be the very last element of our matrix. So we've now got our ds, and just make sure they're defined, and d. So now we can do our right diagonal. So we'll take our rn, as we previously defined. It is going to be our scaling added on with the dropped I. So the dropped I, if I just run just that part, you can see is just up to 0 up to 17. And then we're just adding on to each of these. We're adding our scaling 0, 6, and 12. So you'll see that, say, the 0 will be added to the first item of each column, the 6 to the second, and the 12 to the third. So if we look back at the original matrix again, why is it that we have the second one here 7 when we said it was 6? So this is 0, 1, 2, 3, 4, 5, 6. So this is the sixth index, but this here is telling us that it's 7. The reason is because, again, remember, we're going to join on our extra column of zeros. So this scaling has already accounted for that when we join that on. Because if you think, we've already pre-joined it on because it's in this rn variable. So whenever I actually index into that, then that is correct. So if I look at the first column here, 66, 9, and 86, and that's 66, 9, and 86. We will mark that with our D. Finally, on to the left diagonal. We need to essentially use a slightly modified version of the scaling factor that we've used for the right. So it will be ds and then plus some alteration. So the alteration is x minus 2 times till x. So if I run this gives me 3, 1, minus 1. And if I run just the 2 part, you can see that's 0, 2, 4, and this essentially gives you even numbers up until whatever number x is. So why is that what we need to change the scale? So if you think about the right diagonal, it would have been 0, and then 6, and then 12, without the not including the 0 column. That's accounted for anyway, so don't worry about that, just to simplify it. If you think about then the left diagonal, it's actually going to be 2, the middle one will be the same, and then this is actually going to be 10. So it's essentially like you've minus 2, or you've added 2 to the first one, nothing to the second one, and then minus 2 from the third one. And if you it will depend then simply on the size of x. So if I was using 4 items here, going right down to here, then the difference then is going to be slightly bigger between these ones. It's actually going to be like you're minus 3, and then minus 2 from this, adding 2 to this, and adding 4 to this, or adding 3 to this, something like that. So it's going to be 3, add 1, minus 1, and minus 3. So it depends simply on the size of, or the length of x, and how many items you're going to have. But this essentially creates that. So you think then that if our first one here is 0, 1, 2, we add on 3, gets us to the third one. And again, remember, we're going to be joining on the zeros, and the zeros are going to be added to the left hand side, which is why this index is going to be 0 plus 3 gives 3, which you think was this one, but because we joined the zeros onto the left hand column, it's actually this. Then, so if I actually just run this so you can see these, the next one is 7. So you can see if I go, had the zeros here on the left, I would have 1 or 0, 1, 2, 3, 4, 5, 6, 7. So that would be this value here. However, remember that we still have to add on the actual I values. So this is just to create the scaling. So if I do that, so remember the I values is going to have the D drop part as well, and run that now. So that gives me all of them. You can see that the first one here now is actually going to be 0, 1, 2 plus 3, 7, 11, which gives us the actual indexes that we need. So looking at the, so if I actually create the list with the column just so we can see it a bit better, you can see that this is going to be 0, 1, 2, 3. So this is going to be the first left value item, and then 4, 5, 6, 7, and then 8. And so we're wanting these 3, remember, and then this one will be 13. So you can see again from this that this is the left diagonals. All that I need to do now is to actually index that into our raised version of 0 join each right n, and then run that, and then you can see this will match with our, if we look at the first one, it's 13, 9, 23. So all we need to do now is to actually join all these together, do the product, and then take the max. So I'm essentially going to just paste in the solution here. Sorry, not over the top of the left diagonal. So just mark this with LD. So you'll see that this is all the setup that we had before, and then these 4 are the diagonals that we had before, the directions that we had before, so the horizontal, vertical, and the 2 diagonals. And then all we're doing is doing a join each both over this list. So each of these four items is a list of three lists, and then if we join each both, that means we're going to take the first list of the first item and join it with the first list of the second item and the first list of the third item, etc. So once we do that, then if I just maybe even run just this part, you can see that gives me three lists, and they're quite long because it's all of the four joined together. And then we do prod. So remember, prod is the product, and it works column wise. So we get a product for each column multiplied together, and then we just want to find which one's the max. So that is our S1, and then I can actually run that on the actual inputs. So the inputs I have saved, the input grid, I'm just going to save it into this end, so it's on a file on disk, so you can actually see then. If you use on the Git, it will be saved in one of the files. So you can see here I've loaded it in, and remember that for the question it wants the four adjacent elements, so our x is 4. So I do x1 on n and then x and run that. You can see that that is the answer. So yeah, that's everything for part 1. So check out part 2 if you want to see the solution 2 and then the performance comparison between both solutions. And thank you for watching.